Great, thanks. Okay, so welcome to the foundation lecture on neurodynamics. It's like the introduction now really into the methods that are proper to this course, that are the core of this course. So previously in my introduction, the Breitenberg tutorial, I referred to activation, was sort of the idea that sensors transform intensities, physical things into inner variables, activation variables. And so now I want to talk a little bit about what those activation variables are. And I briefly then said they are maybe membrane potentials or the spike rate train of neurons. Today I'll elaborate that a little bit, but we will get a fuller picture when I introduce fields. But now I'll just link it a little bit more to neural activity, and I do that really to understand how activation evolves in time, how to get to the dynamics of activation. So remember, activation can have effects. It will have effects ultimately when sent to actuators, to muscles, where it will be transformed into movement or force, something physical. And that's sort of an important notion, that ultimately what activation means is ultimately assessed by the effect ultimately on behavior. So we always talk about downstream with the idea that there's an overall direction in which activation ultimately leads from the sensory to the motor surface. It's not actually a feed-forward connection network at all. It's a very strongly recurrent network that we'll look at. But the ultimate currency of what activation means, for instance, also the metrics, how much difference in activation is important, has to do ultimately with what kind of effects it has. You can easily see if this is the range of, let's say, speeds your wheel can turn, or actually, let's say, forces your muscle can generate, then you might think, well, this is the range of activation that you are interested in, right? If if there was only a very small subinterval here that is physically realizable, it would be the corresponding subinterval of activation that plays a role. So the units of activation ultimately, so far are arbitrary, and ultimately they will attain meaning by what they do downstream. That will be an important theme. So we're using this word activation in an abstract sense. That abstracts away from the neurophysics, and I'll give you this little tutorial later about neurophysics. And it is, so the way it's actually operationalized is really refers to the sigmoidal threshold function. You will see in a moment that whenever we write down neural networks, the activation that represents one small population of neurons, it will turn out, it's always small populations of neurons, but sometimes I will talk now about a neuron, but it will be actually jargon for saying it's a small population of neurons, really. So the activation of such a small population ultimately has an effect on anything else only after it passes through a threshold function. Sometimes we call that G in the book chapter. It's called G of U. In other contexts, we call it sigma of U. It's just some convention. It's a threshold function in the sense that it goes to 0 for negative values of activation and goes to some constant for positive values of activation. So it's monotonically increasing with limit cases that are constant. This is, for instance, not a polynomial. That actually plays a role. It's a transcendental function for those who know these kind of mathematical things that has some impact for the mathematics of this. Polynomials always go to plus or minus infinity at plus or minus u to infinity. So I was just hinting that activation as such is an abstract thing for us, so it has arbitrary units. And so what are relevant ranges? Many of the models we'll write down, you can operate in different ranges. You can take activation to vary from 0 to 10, from minus 10 to plus 10, let's say, or from minus 100 to plus 100. The meaning of these ranges is ultimately determined by the sigmoid function. You can see if you have that steep function, it's this little interval where all the action takes place. Nothing much changes over here or over there. And that determines what are relevant values of activation, while this broader sigmoid suggests that a different range of U makes functional difference. And so ultimately, as I hinted, it will be when that sigmoid is handed down to the motor system, that it will really attain meaning. So that initially is a little bit of an obstacle. I'll briefly refer to neurophysics again to make it less mysterious. But in the end, you will see that it doesn't really matter much, because we will build up systems that consist all of the same kind of activation variables, and then the units of all these different subsystems are all comparable. It's actually a problem in neuroscience, well-known problem of normalization of how that actually happens when you have populations that have very different firing rates. How do they actually talk to each other? But I will not be going very deeply into that. So here, just a brief link to neurophysics. Again, I'll give a tutorial about this later. So in one possible view would be that these activations are really membrane potentials. I explained this afternoon that that's what characterizes neurons. So you can record these membrane potentials by directly sticking an electrode into an axon. And then you will see that the potential is negative compared to the cellular environment. These are the negative potentials here measured inside the membrane. If you electrically excite the axon somewhere, like with a little pulse, then you see a time course. You see the time course is not as sharp as the stimulation, it's electrical stimulation. It's sort of a low pass filtered. In fact, if you look in detail, it has sort of exponential relaxation, and you already know what that means. It must be a linear dynamics in the first approximation on a time scale of about 10 milliseconds. And that means it is mathematically described by something like that. You're familiar now with a linear differential equation. U dot equals minus U. U is the letter we use for activation. I put the tau here on the left, oops, rather than divide by tau. You could also put it here as 1 over tau would be here the slope of that minus U term. And so this linear dynamics has exponential solutions, as you've exercised also last week. And it's based on the fact that, so as a macroscopic description of what these membrane potentials do, because they're often exponential, it's not so obvious actually in this plot, but it's actually very reliably exponential if you do intracellular stimulation and intracellular recording. So that is, in a sense, where that form of the dynamics comes from, and that actually also fixes the time scale. The time scale is, how steep the exponential is, and you in last exercise you actually played with that, and that time scale is about 10-20 milliseconds in the nervous system. So we'll elaborate in a moment later that inputs are actually additive contributions to this dynamics. I'll explain this constant that we add just to calibrate where the threshold is for you. So this would be a very crude description. This is so-called integrated fire description of the membrane of a neuron. And you already see here in this picture that there is some nonlinearity in here, in that when you're stimulating by a larger amount, you get a nonlinear change from responding proportional to the strength of that stimulus to then having generating a spike, a suprathreshold event. So here you see the spike is, the stimulus is over, but there is a whole, still an increase in potential that's no longer driven by input, that's actually driven by the membrane itself. And I explain the spiking mechanism again a little later today. So that's only these spiking events are actually transmitted to downstream neurons through the synapses. And that's sort of the cellular level of where the sigmoid comes from. Different stimulation levels of stimulation or different activation states may be reflected in different rates of firing. So this would be, for instance, a low rate of firing that would reflect a low level of activation, or be mapped onto a low level of activation. This would be a high rate of firing. Different firing rates could be mapped onto different activation levels. So another way, in other words, to think of the abstract variable activation is as firing rate. If it is firing rate, it would something that can only be positive. So we're not actually using that picture, but there is a way to transform all the mathematics that we'll be using in this course into this picture. Sometimes it's called the Wilson-Cowan image. And it's sort of a one-to-one relationship. You could also use that. We're not doing that. So these the spiking mechanism and the associated dependence of firing rate on the inputs is replaced in the picture I will be using by just a sigmoid threshold function, as I hinted at earlier. And 2 or 3 lectures down, you will see it's actually a effective threshold for activity in a population. It's not a single neuron that is described in that way. Okay, so that's just the little bit of motivation for where that equation comes from that is foundational for us. In the book chapter that I will be inviting you to read with the next exercise, there is a somewhat more abstract justification for this description at the population level. I call that the Einstein argument. It's about diffusion and stability. And I'm inviting you on that exercise sheet to think through that. But in this lecture, I'm not elaborating on that. I make a special point about that because, as you might already intuit, this is not the form of a neural network, right? This minus U term is not. You will later see that the neural network parts are inputs that are added here as additional driving forces for this U dot. So the minus U is ultimately inherited from the membrane. It gives the membrane this property of transducing input into exponential time courses, pieces of exponential time courses. So it's quite important. So if I postulate that this is the shape of an elementary activation variable, so a dynamic shape, so activation of any subpopulation we look at ultimately is described by something like this, then we have neurodynamics, right? Then we already have a dynamic system. Now this activation is just one, it could be thought of as one neuron or one population of neurons. So we're not even talking about a neural network yet. We're not talking about receiving input from other neurons or projecting on other neurons. So just isolated itself, it already has a dynamics. We call that a neurodynamics. And that is a dynamic system. So it is evolving continuously in time in a way that is predicted by the present state. Now, the present state is in the nervous system never arbitrary. It always comes from somewhere, right? Maybe when you were born, you had some initial state, but since then, you're always in a state that is actually an attractor state from your previous set of inputs. And so it's, and you already know, of course, that dynamic cycles have attractor states. So if this is the plot of that, the graph of this dynamic system, then the zero crossing here is where U equals H, right? U dot would be 0, U equals H. We're conventionally considering this H to be a negative number so that it intersects here at a point that is to the left of this axis. It's a negative number because we're considering this the off state, no input state. And then this neural population is supposed to not transmit anything to downstream neurons. And that will be because it's below the sigmoid, the threshold of the sigmoid. So conventionally, we put the threshold of the sigmoid at 0 here. So we're choosing a value here somewhere on the left as being the resting state. So nothing is transmitted. That's why it's always here shifted to the left. So it's a dynamical system. In this same sense, you learn that any initial level of activation determines the future with this typical mental simulation picture. If you're here, you have a negative rate of change, you're decreasing. If you're here, have a positive rate of change, you're increasing, right? And that's why you would be converging to the 6 month. That is an attractor. I think I have an extra slide for that. So you would be converging to that. So that's why I'm saying, and the fixed point is essentially a constant activation level as a solution, the stationary state. And so I'm saying, if this is really the description of any kind of subpopulation in the brain, then they are always in an attractor state unless the attractor state just is shifted or destroyed. Now we'll be coming to that. So you're not really thinking the nervous system that you set some initial condition and then see the relaxation. No, it's always in an attractor in this kind of fixed point attractor. It could be the resting state. Unless there is something that moves the attractor around, then the system goes there. And so that means that the time courses of activation are described, are sort of structured by the attractor. So if you come from different initial states, in the sense somewhere else there was an attractor earlier, and now you're you're exposed to the situation, let's say without input, then you will be converging to this attractor with an exponential relaxation. And the time scale of the neurodynamics is that universal parameter that will be keeping constant pretty much throughout our thought. There is actually now work on what are characteristic timescales in neural populations in the brain. This uses an image of correlation time, which is a little bit more advanced concept, but one can estimate these kinds of timescales through by looking at how correlations decay. And then you find that cortical areas that are close to sensory inputs have timescales that are a little faster. They're actually slower than individual neurons. They lie on the order of about 100 milliseconds, and they become slower as you go higher in the brain. For instance, the frontal brain, you have the highest correlation times like that. So times that it takes for correlations to decay. So for instance, up to maybe 250 or so, which is theoretically interesting. It's not something that we're concretely using in anything that we'll be touching in this course, but there is some interest in thinking about what that means. It's sort of about integrating signals with very many different timescales. To integrate those, you have to make timescales slow so that multiple signals can overlap in time. Good. So a single population with nothing else is, of course, very boring and would be just in a resting state. And what we're interested in is, of course, if there are inputs. And so inputs are, in the neurodynamic picture, additive forces. So contributions to the right-hand side of this equation. You could say they specify rates of change, but they are, together with this minus u term that makes the attractor. So, for instance, if I have an input, I'm writing this as a time function because this could maybe come from the sensory surface ultimately, and maybe by changing or turning off on the light or changing something environment, I could vary the activation that arrives at a particular population I'm looking at in a way that is dictated from the outside. It's an explicit function of time, while u evolves as a function of time just because it is a solution of this equation. So this is autonomously generated while this is imposed from the outside. So inputs are called excitatory if they add positive rates of change. So if this is a positive number, and if it's a negative number, or if I put a minus sign here, those would be inhibitory inputs. That is, they make a negative rate of change. They drive the activation into the direction of less activation. So what an input like that, if you think of that, this is a constant in terms of it doesn't depend on u, right? If you plot the right-hand side as a function of u, then the minus u, depends on u, has this negative slope. The s is a constant relative to u. So if you add that constant, you essentially just shift that minus u function up by the amount s and still retain the shape of that function. So that amounts to just shifting the attractor, right? If this is your attractor, now it's been shifted to the right. And to the right here means to a positive level of activation. You can easily compute that attractor analytically by saying, okay, where is the fixed point? U dot equals 0, put the u to the other side, then u equals h plus s, right? So this is at h plus s. So here I'm showing what the consequences of that for the activation state. So I'm assuming that initially input was 0. So I was sitting in a attractor at u equals h resting level. And then I'm turning on that input abruptly in a step-like function, most extreme case. And what will happen is that the activation will then emerge as an exponential relaxation toward the value that equals to h plus s. So it's lowered below this level of s by h, which is a negative number. That's where it will asymptote. That's where the time scales comes from. The activation that's going to be transmitted to downstream neurons is slightly different. That will be the sigmoidal function applied to this u. So I haven't written down any units, but this would be the amplitude of the sigmoid. That will be 1, and the others have arbitrary size here. And so you see only when activation crosses 0 about here, the sigmoid starts to turn on. It's a pretty sharp sigmoid. So within this range here of activation, sorry, this range of activation, it has saturated. And so all of those are mapped onto the same output of that system. This is sometimes called output in our jargon, output of that neural population. In this picture here, you see what actually happens is that you're sitting in this previous attractor. That's what I said, you always sit in an attractor somewhere. Now you're sitting in this resting attractor, and suddenly your attractor shifts because the input changes. And what drives you there is actually the minus u function, right? Because now if you are here, you look up your rate of change, it's up here, and that means negative, sorry, negative puts you here to the right. Sorry, it's positive, so increase of u puts you to the right, and so you're running down until you're in the fixed point. So the minus u term is very important to bring about the change, right? You could think the input just shifts the attractor around, and then what puts you to the attractor is really the minus u term. In fact, this Einstein argument you will be going through suggests that if you were to drop this minus u term, then there wouldn't be any mechanisms to make u go toward a particular value, because the input would be just additive and you would just grow, but beyond any limit, for instance. And so that would be a problem. Yeah, so in neurodynamics, the inputs don't set the outputs, they set the rate of change of the outputs, and then the output change is arrives from the interplay of the input and the minus u term. Yeah, so you can also think of this as a low-pass filter for those who know the notion of filtering, for instance, engineers, because you could say my input is this time function, a very abrupt time function, and my output is a somewhat smoothed time function. And if you think of the sigmoid as the output, this would be the smooth function. So it's a little bit smoothed, and the time scale of the dynamics, the tau here determines how much smooth that is. The sigmoid actually also contributes to that. So that's just one neural population without getting some external input, without any recurrence. I was going to introduce you to the simulator with which you can examine that yourself. I have to stop screen sharing for that. So if you go to the webpage of the dynamic field theory module, this is also listed on the next exercise sheet. You can, under learning DFT, go to live simulators, and there's the Two-neuron simulator. It's a online Java-based simulator that Raul Greben produced for us. And it actually has two neurons that are illustrated here, which we'll need later. Now we're just interested in one neuron. So here you see the neural dynamics. It's u dot against u. You see here, this is the zero axis. That is a zero axis. So it currently has a attractor at -5 with a negative slope. And this is the time course of that neuron. It's actually sitting in the attractor, and that's why you don't see anything moving. But I can actually, with these buttons here, change something about that neuron. For instance, I can change some stimulus strength, some input to that neuron. And by shifting that up, I can supply a stimulus. You see, I shifted it up. And you see the green line is that function. You see what happens. There's an exponential relaxation to the new state. Let's shift it up a little more. And you see the low pass filtering there. Also see what happens if I go back. Okay. And I think you should still see these slides, right? Please yell if you don't. I'm not having a different mode of sharing. So that's a single neuron just getting input from the outside. That has this very simple low pass filter property. A single population, let's say. Now, the next simplest neural network is just one population or one neuron talking to itself. That's certainly the simplest neural network you could think of. If you think of neurons, it would be one neuron that just couples to itself. That would be the only neural connection in here. And we're considering the case where it's an excitatory neuron, and so it's coupling back onto itself in an excitatory fashion. So that means it shows up here with a plus sign, and this is a positive number. And I switched the letter to sigma, sorry about that. So this is the sigmoid. So only the output of that neuron couples back onto itself. Now that's as simple as it may sound, that is actually also quite foundational for everything else that we'll do. So what would that look like? I'm plotting here the negative minus u term, and this is the sigma of u. And so you have to think of adding these two, and what would happen would be that here in this domain is the linear function that prevails, right? So you would get this function is also shifted here. And then on the right-hand side, you would be adding this amount. So adding would mean that instead of continuing linearly, you have here this amount of shift asymptotically for large u, and somewhere in between it has to cross over, right? So it would be roughly looking like this. These plots are not actually ideally mapped onto each other, because here the resting level, it should be, as the resting level I'm adding 0, so this should actually be sitting here. I have a more negative resting level in the second plot. Sorry, I've just noticed that these are done by hand, so these two are not actually mapping onto each other very well. The resting level should be here. Sorry about that. Now that's how this shape arises. This is a nonlinear function of u, as we've discussed in the tutorial, because it's not a straight line. So far, nothing has happened. That is, so far there's still the only attractor is here at the resting state. This is the case without any s, or it will be even a negative s here. And so it's just as it relaxes there, it might be slowing down here a little bit. But of course, we could have different levels of input. And if we now apply this nonlinear function, an input to this nonlinear function, then you see interesting stuff is going to happen. So for instance, when this was the original value, the gray level indicates increasing levels of input strength of S. And you see at some input strength, there is a new intersection with the u equals 0 axis, u dot equals 0 axis, here the u axis. Starts about here, and then it has split into a repeller, you recognize immediately, and an attractor. And then there's a second interesting transition where the repeller disappears again and the attractor on the right persists, but at these values, there is no attractor on the left. These are fundamental instabilities. You recognize maybe immediately these are bifurcations, because here an attractor and a repeller, here actually a repeller arises out of nowhere and then splits into an attractor and a repeller. That's a tangent bifurcation. And then the second bifurcation is where this repeller collides with this attractor and lifts off, and that's a reverse tangent bifurcation. In the middle, the dynamics is bistable, and that means that now it matters where you're coming from. So if you're initially in an attractor with some positive level of activation, then you're going to converge to the plus solution, the suprathreshold or on state. And if you're coming from an attractor with some negative activation, you're going to converge to the off state, to this attractor, some negative state. So this is a first case where the input S no longer, yeah, this is a constant input. Some input brings about that dynamics, right? Different inputs make different lines like that. I'm picking out one particular line, one particular input. So at constant input, you have different states depending on your previous state. So input doesn't uniquely determine the output. The current state plus the input determine the current, the output, the response of that neuron. So that's already a deviation from a feed-forward network. This is a strongly recurrent neural network, strong in the sense that this contribution here, the shift from the off to the onset, is not negligible. So the two instabilities here are the one here on the left, where a repeller and an attractor, collide. This, you've studied that. That is the detection instability. We call it detection instability. It's a tangent bifurcation. The unstable and the stable collide as a function of stimulus strength. And then beyond that, locally around the state, there is no more fixed point. There is that other fixed point, and the system will actually go to that other fixed point. That's a non-local phenomenon. That's not captured by this local bifurcation analysis. We call it detection for that reason, because if you're in this attractor, the off state, then if you think of this neuron population as representing something, it represents, let's say, light input or a certain motion state or whatever it is, then this sitting in this attractor on the left would amount to the neuron not projecting to downstream structures, and so what it stands for has not been detected. It does not vote for what it has been, what it stands for. While if it runs through that instability, it would, for instance, if you switch to this state, it would now run to the attractor at the positive level of activation, the on state, and so it would signal now to the downstream structures that it has detected whatever it stands for. That's why we use that word detection. The transition from off to on for a neuron would be a detection. And again, off to on means below threshold to above threshold in terms of transmitting through the sigmoid activation to downstream structures. The other instability is the reverse detection instability. That is, this would be something that's functionally important if you're in the activated state, because let's say previously you've switched to the activated state, and now you're lowering input sufficiently for the attractor and the repeller to collide in this reverse picture. This will be the local picture here. And then so ultimately this repeller disappears and you would be running to the off state. And that's why we say reverse. This would be when you are in a state that represents a detection that the neural population is active, how the neural population would stop being active and go back to being inactive. So together, these two instabilities set up a bistable regime. So if you were to vary input S to this population monotonically, for instance, let's say as a linear input in function of time, you would be originally sitting in the off state below 0, tracking that is, the attractor does move a little bit to higher levels, but it would always stay below 0 until it runs into the detection instability where it would switch to the on state and would stay there. If you then were to run through the same input in the reverse direction, I plotted this now as a function of negative time, but with the understanding that at the same time, in the two cases, you have the same input. It's just where you're coming from that's different. And you will be staying in the on state until you hit the reverse detection instability, and then we'll be switching to the off state. And so this is what physicists call hysteresis, the signature of an underlying bistability, and that's also very fundamental. You will see this many times through the course that we'll be using this principle. And we believe that everywhere in the nervous system, decisions to activate, to initiate, to create a thought, create an instance are always characterized by this kind of instability. Okay, and I was going to simulate that again with that little web simulator. So the same neuron can be used to illustrate that by activating self-excitation. So with this button, you see I can vary the size of this, for instance, like this. Now, this would be still the neuron sitting in the resting state at negative levels of activation, and there is no new attractor. See, if I now give some input, there is a new attractor that forms here. This is the new attractor. This is the repeller. You see this is the tangent bifurcation, right? Where there's touches and then they split. But the system doesn't notice that. It's just sitting here in the off state, in the negative state here. The negative state has moved a little bit. That's why you saw that initial transient, but it's still below 0. And so nothing happens. The system isn't even aware, if you want, of that new attractor until the state we're sitting in becomes unstable. So here we're seeing the attractor and the repeller approach each other, and they will ultimately collide. And just about now, and there you see it switches. You see now you already see a feature that I find very important, that at some point the event where the bistability, the instability brings about a switch to the on state emerges. So for instance, if I were to just vary this input, let me reset this here. If I were to vary this input in a time linear fashion, I can just simulate that by moving this slider at a constant rate, there would be a particular point that emerges from the dynamics. I moved it too fast, move it very slowly. See the tracks and so on. And so it's all a linear function, but then suddenly there is a nonlinear function. See, that's where it happened, where the nonlinear function occurs. And so that's the event creation. So the detection event emerges from the instability. And then the reverse instability, I'm sitting in the off state and I'm reducing input, and then you see the repeller collides with the attractor, and then the system switches to the off state. It's actually only near these instabilities that stochastic decisions occur. You can actually simulate that here by adding noise to the system. Noise is just, sorry, oops, this is not what I wanted. So if I add noise to the system, you see that here. We don't plot that here. The noise is a contribution to the rate of change. So it's just like a stochastic input. And so it's fluctuating around 0. And that doesn't really make much of a difference because fluctuating around that 0 state, except that if we're at an instability or near, then a stochastic event can lead to activation. Then the noise is amplified by the dynamics. And now, it's sitting in an attractor state and it will never, theoretically, in infinite time, it could switch back, but it is very unlikely for it to switch back, while it is much more likely to switch out of the state. So different states with different distance from an instability. This one is very close to an instability. This one is not. React differently to noise. So stochasticity, random decisions, random selections, random thoughts that come up into your mind, they occur due to instabilities. It's not the noise per se that does that. If you make noise so strong that you can have random activation patterns, then you don't get any coherent dynamics and coherent states. So what happens is that there's a balance between noise and stability that limits the effects of noise, except at an instability. So the instability is also critical for stochastic decisions to arise. Okay. So back to the simulation. Now the next more complicated neural network would be two neurons or two populations of neurons. If I were to couple these two neurons excitatorily, nothing special would be happening because a single neuron self-exciting and two neurons self-exciting have sort of the same dynamics. In fact, I think next week or the week after, we will be talking about dynamical fields, and they are essentially continuous populations of neurons, and we will be talking about peaks of activation, as I hinted in the introduction. In the self-excitatory nature of a single neuron or a single activation variable here, you will see is actually a shortcut for talking about excitatory interaction within a little group of neurons. So one neuron or a group of neurons excitatory coupled has the same dynamical behavior. They have this detection instability and the reverse detection instability. So I'm looking at a different kind of coupling to come up with some qualitatively different dynamical property, which is selection or competition. And that's when one of those neurons or neural populations is inhibitorily influencing the other and vice versa. So this little full circle is sometimes used in neural network diagrams to indicate inhibitory coupling. In dynamical terms, it really just means that the other neurons, I'm looking at neuron number 1, the other neuron contributes to the rate of change of neuron number 1 with a negative number. There could be a constant here, which I dropped, but it makes a negative impact. And conversely, the neuron number 1 contributes to the dynamics of neuron number 2 with a negative number. And I assume here that these constants here in front of the sigmoid are both 1, so it's a negative, it's a symmetrical form of coupling. It doesn't have to be symmetrical in general. So that's the notion of inhibitory coupling. I said neuron, it will be a population of neurons. So that has already quite interesting dynamics. It's not so easy to visualize that. Just for the jargon, neural network people talk about connectivity, a pattern of connectivity. This would be a reciprocally inhibitory connectivity, while physicists talk about coupling, and sometimes neuroscientists also use that term. It's really just a special case of connectivity. It's just connectivity that is between different neurons, so that it has an aspect of recurrency, right? You could think of this neuron affects that neuron, and that neuron affects this neuron. So that's a loop, a recurrent loop. And within recurrent systems like that, we use this physics jargon of saying it's coupling. It mathematically is the same thing. It means that the activation of one shows up in the equation of the other. Those of you who are mathematically skilled will know that if you have linear dynamical systems, you can try to decouple them by going to the eigenmodes, eigenvectors, so that you cannot just read from the equation whether something is coupled or not. It's a question of how you represent these subspaces. But in nonlinear systems, that's not the case. There's no way you can get rid of this coupling by a coordinate transform, because this nonlinear function cannot be eliminated by diagonalization. I say this just to the specialists. Those who don't know that, just take it as at bare value that showing up in the equation of the other variable means you're coupled. This would be mutual coupling, even symmetrical coupling. Okay, and so one intuitive way of looking at that is of thinking of the other neuron as being some form of input. It's just sort of a heuristic picture to get intuition. So for instance, we could think of the neuron number 2 or activation variable number 2 to be the input for the activation variable number 1, and just assume that U2 has some value. For instance, U2 has a value that is positive. So its sigmoid returns, let's say the asymptotic value returns a 1. And so the idea would be that the neuron number 1 dynamics would be this light gray line if neuron number 2 was off, was not providing any input. So just this part of the dynamics, right? And that will be have a fixed point at U1 equals H plus S1. That will be this fixed point. And now I'm assuming that neuron number 2 is on, and on means the sigmoid returns -1, and this would be then this inhibition that the system supplies. I should have added here to this equation C12 as a strength here in front of it. I have to correct that. So that's why it says it shifts the attractor to the original attractor minus this inhibitory strength, minus C12. So it's actually along this axis that it shifts that, and it shows up here in the attractor being now, in this case, below 0, if I assume that this amount of inhibition C12 is sufficiently strong. And so you see what would result that neuron number 1 has to be off when neuron number 2 is on. Neuron number 2 would have that kind of dynamics being on. This is a consistent description, because if neuron number 1 is off, is below 0, it does not contribute to this equation. So neuron number 2 is governed by this equation. And so if I assume that S2 has a value where this is positive, and therefore sigma of U2 is 1, then the assumption I made is consistent with the outcome of that assumption. So that's a kind of a mental way of how you can determine the attractor by sort of mentally, by hypothesis testing. You see, there's nothing in this discourse that where U2 is special. So you could also just assume U1 was on and then derive in the same way that U2 would have to be off, assuming, let's say, that these coefficients here are the same as I indicated in the equation. And therefore, you see this is going to be a bistable system as well. It will be bistable in the sense that one neuron can be on and the other off, or vice versa. These are the two states. These are two competitive states. We call about that, you can say it's a selection decision, a competitive decision. and selection in the sense that whatever U1 stands for can be activated, and then whatever U2 stands for is suppressed, or whatever U2 stands for is activated, and whatever U1 stands for is suppressed. So if you have two things, let's say one neuron stands for the color red and the other neuron stands for the color green, then you're going to make a selection decision which of the two colors you're going to perceive or store in memory or act on, like for instance, direct your motion or attention to. Which of these two will be realized will depend on the input strength, for instance. So if you're giving a lot of input to neuron number 2, so S2 is very large, which would mean the attractor is very far out here, then activation of the neuron 2 will rise very quickly. This is something that you will be invited to study in the exercises. And because it arises very quickly, it will start to have an inhibitory influence on the other neuron before that neuron can become very activated. And as a result, you're going to run to this solution where U2 wins and U1 doesn't. And that's sort of a special case of a very general picture that input advantage is translated into a temporal advantage, and that is translated into a competitive advantage. The competitive advantage comes from the fact that you're only having a competitive influence on the other neuron if you're above threshold. So if you reach threshold earlier than the other, then you have competitive advantage. You can begin to inhibit your competitor before the converse process takes place. More input and less input translates in neural network terms into a better match. I haven't really explained that. We'll get that much later. That the effective input strength depends on how well the synaptic pattern matches whatever your inputs is when you go beyond a single neuron and have a whole neural network. So you could say the match of your synaptic connectivity pattern to an input pattern determines the rate of increase, and that determines your competitive advantage, and that's how you're going to select the winner. Right? And all the neural networks that you are familiar with that, for instance, make categorical decisions are essentially based on this kind of mechanism. Many neural networks, people don't actually put the competitive dynamics into the model. They just read out from the outside which neuron became most activated. But if you make the system autonomous and you don't have someone to read out the activation pattern algorithmically from the outside, then it would be this kind of mechanism that does that, and it would translate this difference in activation level that comes from a difference in input strength, comes from a difference in match, into a competitive advantage, and therefore it would make a selection decision in this bistable sense. I want to illustrate the same idea again in a somewhat different way, mathematically a little bit different, because that is a very useful mental picture. That's the vector field picture, right? You remember in the tutorial I said that dynamic systems can be generally formalized as vector fields, and I make this concrete here. This is useful here because we have two neurons. I use this jargon now to say these are neurons, even though they're little populations. You have two neurons, two activation variables, and to plot their dynamics, you would have to plot four things against each other, right? U1 dot, U2 dot against U1 and U2. So that four-dimensional plot isn't easy to make, and a very good visualization is to use the mathematical notion of a vector field, where you could say the right-hand side of the equation, the rate of change, is a vector in the same space as the state space. So U1 and U2 are here, you span the space, and every location space, I draw a little vector that has a U1 component that is equal to U1 dot and a U2 component that is equal to U2 dot. Specifically, for instance, if I take this particular level for U2 and just look for how this varies as a function of U1, this should be U1, then what I'm actually plotting here are these vectors along the U1 axis whose length reflects the rate of change in U1. So when you're far from the fixed point, you have long vectors. When you're close, you have small vectors. Here you have zero length vectors, and the direction is toward this fixed point. So the vectors along this line are essentially the vectors along one dimension. And essentially that's true everywhere. So the vectors along any other line, the U1 component is exactly the same. And similarly, in the other direction, in the vertical direction, the same. I haven't plotted that separately, but the same logic applies here to the vertical component. You can almost, if you follow with the eye, you just follow these vectors along the horizontal, you see that the length of the component of the vector in here in the U2 direction does not depend on where you are along U1. And so this is actually an uncoupled case. These are just two neurons that have both have this simple dynamics. I'm just superposing the vector fields along one axis with the vector field along the other U2 axis, and then you get this kind of picture. This vector field representation captures the dynamics very well, because you can theoretically see that the paths, the trajectories of activation of the two variables, driven by time as the parameter, and the path is just plotting it in the U1, U2 state space. The paths are really just curves that are tangent to these vectors. That's actually the definition of the tangent, is the rate of change, the vector as a function of the index that describes the path, and that's time. So you can literally see here that following these vectors, you will be always converging to the attractor. This is the attractor in the off state. If you give input to these neurons, for instance, shift the vector fields to be focused to converge on a positive level of activation, the same for the two neurons, you would get this conversion vector field, and that would be both in the on state, right? They would be in this right quadrant, which has both neurons activated. So that would be without interaction, just the two neurons uncoupled. Now, when you couple these two neurons, you apply the sigmoid function. Well, only the activated neurons participate in interaction. So only here in this upper quadrant will something change. Everywhere else, it will look very much like it did here, because everywhere else there is no interaction. And it's not quite true. And this picture actually shows it correctly. So for instance, if I'm looking at the influence of neuron number 1 on neuron number 2, I call these now sites, because I'm thinking of a population. There are different locations in the population. So the population 1 inhibiting population 2, that means it's a contribution to the dynamics of 2, so negative, making a negative rate of change, but it's only non-zero where U1 is positive. So only in this right half does it show. In fact, the length of these vectors would be exactly described by the sigmoid function as I move along U1. And analogously, if you look at the influence of the neuron number 2 on neuron number 1, that would be something that is negative for U1, so it pushes to lower levels of U1, pointing it to the left, but it's only present where U2 is positive, so here in this upper half. And again, the length of these vectors are described by the sigmoid. And this is just summing these two contributions, and that will be capturing really the effect of the interaction. You see, it's a very clear picture where you see the interaction as a vector field. And so, as I was saying, here in this quadrant, it has the strongest effect. It pushes the system away out of this quadrant. Here, it would push it down along U2, and here would push it to the left along U1. You could see that just having this kind of coupling would not yet lead to reasonable stable state, right? Because here what would happen is you would be running to -infinity this way or that way. So to keep it at a constant value, to stabilize it, you need to superpose that with the original conversion vector field. So if you add this conversion vector field that contains the -u term with the input, so that the attractor is here in the plus regime, you add this interaction, you arrive at this kind of vector field. To see what, what happens here is that you get the same vector field as here, because there's nothing in the negative. When both are negative, there's nothing. Here in the positive regime, you have this strong vector field that presses toward lower activation over superposed on a relatively weak conversion vector field. So the strong one dominates and you push to the origin. And here you have a slightly conversion vector field and an opposing vector field. And they make a new equilibrium, a compromise, where there's a new attractor here. And by symmetry, the same happens here in this quadrant. And now you see this is bistable in the sense there are two attractors. There is a basin of the boundary of attraction that is basin of attraction that is anywhere, this line here leads exactly to this unstable state, and that line leads exactly to that state. And so if you're anywhere to the right below that state, you're going to converge to this one. Anywhere to the above, to the left of this one, you're going to converge to this attractor. So this is the attractor where U1 has a positive level of activation, U2 has a negative level of activation. This is where U2 has a positive level of activation, and U1 a negative level of activation. Now it's very direct representation of the outcome of competition. Now this is where both would be on, U1 is on, U2 is on, both are off. Now this picture is particularly useful to see what happens when you have this different in match. So this is, no, before I go there, sorry, I want to just say what happens, how the decision is made. And to see that, you have to be aware that before that stimulus is presented, the stimulus that here, activates both of these inputs, the symmetrical stimulus gives both inputs systems the same strength. Before that is presented, you are potentially, you have no stim input, let's say. You are sitting, therefore, in this resting state. And this is the dynamics you have. And as you remember, the stimulus, the input, is a change to the dynamics, change to the right-hand side. Here means a change to the vector field. So what happens when you apply the stimulus is that this vector field is transformed into this vector field. So now what you have to think, to understand what happens, you have to think of what your previous state was. Your previous state was you were sitting here, so that means you were sitting right here. And you see this symmetrical case is the one very special case where you're sitting exactly on the boundary of the basins of attraction. So here you will make a stochastic decision. So if you're sitting right here, you could either run into this attractor or run into that attractor, and it will matter if there is a little noise, if you hadn't perfectly relaxed yet, or if your input strengths are slightly noisy, then you will get onto one half of this line or the other half. And once you are a little bit away from this line, noise is not easily going to take you back because the vectors point into this direction. So then you will be amplifying that noise and going to the corresponding attractor. So that's a special case, the symmetrical case. It's a special case, and that's where random decisions, selection decisions may arise. We'll see that later again in dynamic field theory. In general, this is not so common because these symmetrical cases are very rare. It's rare for multiple patterns matching exactly your knowledge, which is in your neural network connectivities. So generally, there will be one pattern that gets more input than another pattern, that matches better. And so this general situation is plotted here, where I'm saying that the population U1 gets larger input. So this is a much larger activation level than this here, in this direction, right? That would be an asymmetrical case. Again, superposing this with the competitive component of the field, the interaction, you get this picture. And you see now there's the boundary between the basins of attraction is no longer at the symmetrical axis, shifted toward the attractor that is less stable. So the U2 winning, U2 is the one that gets less input. U2 winning is not so far from the boundary where U1 is winning, or other way around. Then more initial conditions lead to the attractor where U1 wins than the initial conditions where U2 wins. So in particular, if you think that you're initially sitting in the neutral state, when both neurons are off, you're sitting somewhere here, now you see with overwhelming probability, you would actually activate U1, and some special case where noise would take you across this boundary and go to the other attractor. Now, so in general, these stochastic decisions will be very rare. You will have a unique answer, even though there are multiple possible states. And I will give you an example of that a couple of lectures down. Okay, so I was going to simulate that. And I can simulate that here in this picture by using yet another button. I have a button for connection strength, and this is the influence of U2, this neuron, onto U1. I can make that negative, for instance, like this. And then I have a button here for the connection strength of U1 onto U2. And I also make that negative symmetrically here. So far, you're seeing nothing. Actually, this one does have some input here. But other than that, you're not seeing anything because both neurons are below threshold. Here, the two neurons are plotted against each other. So you can very directly compare that to the vector field I just showed you. So far, nothing happens because they're both off. And now I'm going to make one of those neurons on, for instance, just below threshold. And as we go above threshold, you see the inhibition arises now, shifting this axis down. So this neuron is below threshold and that neuron is above. So it has decided, selected that particular neuron. I can give the other neuron the same input. So for instance, here, let's say we put both to 4. Oh, sorry, I moved the wrong button. This was supposed to -5. Let's start again. So both of these are off, and I give this here an input strength, I don't know, of 5, let's say. Let's say 7. Yeah, 7 is good. And this one is on, and this one is deeply inhibited now. And if I give this neuron a similar input strength of 7, everything's symmetrical, but this neuron is off, it's below 0, and that neuron is on. You see it's in the right quadrant, even though everything is symmetrical. And that is because in this program, I cannot apply the inputs to the two neurons at the same time. So I have a temporal advantage again to 1, and then this wins. Of course, that's not really how it happens in the nervous system, where all the neurons get the input at the same time when stimulus is supplied, and then this would be the stochastic case. And I can illustrate that stochastic case by saying, one of those gets much stronger input, like I give this much stronger input, and now what happens is that this, in spite of the inhibition, became activated. It actually destabilized that this selection. This is now a monostable regime, and therefore this neuron is now suppressed below 0. And if I return to a level of value where it's symmetrical, like this, this one stays on, and this one continues to suppress. We're in the regime where U2 won. And that is a concrete illustration here in the model that the competitive state is also bistable. That is, it's a bistable regime where you can either activate one neuron or one selection decision or the other selection decision, but they exist bistably for a certain dynamical regime. And if you're going outside of that regime, you can switch the selection decision, but then you're stabilizing that decision. You're staying in that decision. So here, for instance, you still see this is still a bistable system, right? And so if you initially had maybe a symmetrical case, or gave this more input, and you would be sitting near or in this attractor, you would stay there even though the other one is now more attractive, right? And if you make the input more asymmetrical, you can actually make this attractor fuse with this boundary. This is where the system would become monostable. Under those conditions, only neuron number 2 can win, and neuron number 1 can win, and neuron number 2 could not possibly win. That's when the system switches. So that will be the limit of that bistable regime. This is a bistability in selection that I will discuss in the field case in much more detail. For single neurons, it's not quite so intuitive. Okay, I'll close by pointing essentially to the future. So what we'll see in the next couple of lectures is that with the same underlying mathematics, but just introducing continuously many neurons in fields, we can generate attractor states that realize both of these patterns. That is, they realize detection and selection, and the detection will be critically mediated by local excitatory coupling. We call that self-excitation within a little population. So in the field, we'll introduce a kernel where over shortened distances in the fields, coupling will be positive. And then over larger distances, coupling will be negative, formalized like this. We'll go through that in more detail. And that will realize that competitive regime. So these fields combine the two regimes, and you will see that that does a lot of cognitive function. And in that picture, what we did now was not consider the underlying dimension. I'll introduce that dimension in the next lecture. And instead, we just talked about one neuron or one neural population and another at some distance. And so the inhibition between those neurons corresponds to the connectivity over a certain distance, while the self-excitation that I looked at individually, that will be neural interaction in a close range. And I'll return to that picture when we have the field. I just want to point where that goes. You will find that the detection instabilities, both regular and the reverse, and the selection property, the bistable range for selection, that is actually the main function of the field. Shows up even in individual activation variables. Good, so that actually is already the end of this lecture. I'll stop sharing my field and take your questions.